All right, Fender Productions presents the Atomic Interactions FET simulation. This is going to be very quick. I just want you guys to see something. And then there's another video that I found that will help explain what's going on more clearly than I can right now. But I wanted you to see, let's say we have two oxygen atoms. You know what? I'm going to not use oxygen because you'll be able to see it better if I use... Let's use just argon and argon. The reason I chose that is because I want the graph here at the bottom to be above this axis so you can see what happens at the bottom of the graph. So I'm going to label attractive forces in orange and repulsive forces in magenta. So remember what's in an atom, right? There's a nucleus with positive charges, the protons in the middle, neutrons in the middle, and electrons in the space around the nucleus, according to our data and our reasoning. That means there's positive and negative charges. So what ends up happening is you actually have attractive forces and repulsive forces at the same time. And so what this graph is showing you up here is this graph is showing you how much potential energy there is as a function of the distance between the atoms. So as the distance between the atoms changes, how much potential energy will there be? So how much potential will there be for something to happen, some force to cause these two atoms to move again? I'll try and say that one more time more clearly. This is looking at how the distance affects how much potential there is for the atoms to then move each other even more. Okay, I'm just going to play this so you can see what happens. Let's move it up so it's a little more fun. Okay, so what you can't tell is that this is like a gradually sloping ramp. And eventually, sort of like a skateboard ramp. Like gradually you go down the ramp, and then once the slope of the ramp starts to get steeper and steeper and steeper, this atom will go faster and faster, accelerate toward a bottom point, and then it will eventually the potential energy on the other side will get too big and will start to push this atom back. And so that's when you start to see that magenta arrow start to become really, really big. Okay, so there's a point, if we manually do this, there's a point right here where, because of the distance between the two atoms, the attractive force wins out. So the orange arrow is bigger than the magenta arrow. And you notice where the little rider is. Yeah. You can see where the rider is if we move this like right here. I'm calling this the rider because it's sort of riding this graph a little bit, like a roller coaster car or something. So this, if this were like a marble, you can sort of envision this. If this were a marble and this were just like a depression in like a cement bench, let's say someone was able to sculpt out this like curved hole in a bench, and you just had a marble and you could just let the marble go. The marble's not at the top, or it's not at the bottom yet. So when you let it go, there's a force that's going to pull it back toward the bottom of that graph. Okay, that's going to be the point where the attractive and the repulsive forces are even. Okay, it's the most stable position because the potential energy is minimized. There is the least amount of potential to continue moving in either direction. Sort of like if you had that marble, gets to the bottom of that like cutout in the cement. Once it's at the bottom, it has the least potential to move any further than that. Okay, but as you move the atom over here and they get closer, you can see that the magenta arrow, the repulsive force, is getting a lot bigger. So that means that now there's more potential to push away, which is why the rider moves up again, which is why if we press play, it goes back. Okay, that was it.